Hi, we're on chapter 7. This is atmospheric circulations, and I put up this photograph of a really ominous circulation of clouds. We're going to talk a little bit about how this comes about and get ready to really get into weather forecasting. When we talk about atmospheric circulations in this video, we're going to be talking about local wind systems, like that photograph showed, very localized cloud over a country road. When we talk about local wind systems, we're talking about thermal circulations. These are circulations brought about by changes in air temperature. That's why we studied temperature so much. And you will be able to look at thermal highs and lows on the surface and in the atmosphere. Let's start with what you know first. You know that you had two columns of air in the city. They were identical columns of air. You cooled one of the columns. You heated the other column. That resulted in high pressure aloft and low pressure aloft. And equilibrium moved everything from the high pressure aloft over to the low pressure aloft. That meant that the low pressure aloft was a sinking, became more dense at the surface, and produced high pressure at the surface. And in fact, when we did all that rearranging, we produced low pressure at the surface of this great warm column, and you started a circle of high pressure aloft to low pressure aloft that continued in a circle at the surface. Most of our local wind systems follow this same trajectory. That's why we studied it. And in fact, you can look at isobaric surfaces up to 1 kilometer high, pretty near the surface of the Earth. And you can note that there are some differences in the atmospheric pressures. That means the pressures aloft, moving from high to low. These are warm areas that have high pressure aloft, moving to cooler areas that have lower pressure aloft. And in the same way as in the columns of air in our city, you produce a circular pattern. Check that out. If you need to go over this again, you can always stop the tape. We're going to talk about many different kinds of thermal circulations. And in fact, we're going to be doing some exercises in the back of your chapter 7 on identifying those thermal circulations. So we'll start off with the ones you know, the land and sea breeze at the Jersey Shore. Okay, land and sea breeze at the Jersey Shore is much like the skyscrapers in the city. So you remember your warm skyscraper in the city. It's much like the land during the day, during the summertime at the shore. The land bakes all day long and really gets very, very warm. You know about the soil, the wet soil and the dry soil. And in getting warm, we are promoting convection that is promoting cloud buildup during the day. So in other words, we're promoting rising air just like the warm skyscraper produces a higher pressure aloft. And we know that the ocean is cooler during the day. And so we have denser air over the ocean, and we have lower pressure over the ocean. That's why you have that L there for the lower pressure over the ocean. We know, just like our skyscrapers, that we start aloft from high pressure to low pressure. And then we seem to have a sinking column here filled with all these new air molecules that produces high pressure over the ocean. And we start this circular pattern of high aloft to low aloft, high at surface to low at surface. This is known as a sea breeze because it comes from the sea during the day. See what happens at night. It's a land breeze at night. Let's start with what is high and what was going on. At night, things change around a bit. At night, you have had the ocean warming during the day, and now it's emitting and evaporating air up from the warmed ocean overnight. It's forming a high pressure system at about 900 millibars over the ocean. Because this air is rising, we have high pressure aloft. And conversely, the pressure over land is lower because the land has been cooling quite a bit once the sun went down. So we've got high to low pressure, sinking air, and high to low pressure on the surface. We have a land breeze because the breeze comes from the land. So while the heat was over the land during the day, the heat is stored over the water at night. Always work from aloft. Let's go to the next one. And that's going to be showing you a sea breeze and convergence lift over Florida. We've already reviewed these a couple times, coming in from the Gulf of Mexico and coming in from the Atlantic. It's also driven by a little bit of the Gulf Stream here as well. When these two converge, they will result in convergent lifting, force lifting, and cumulus clouds that top off in the afternoon. So here's another thermal circulation that's complicated by its peninsula location and convergence on both sides for the sea breezes. Here's the convergence clouds that form as a result. Look at the rain underneath. And this is also an example of a low that happened over the peninsula of Florida, sending air skywards. This builds because the air diverges in the upper atmosphere. So the air converges at the surface into the low, sends it up to the upper atmosphere, and diverges in the upper atmosphere, forming that beautiful anvil that you see up there. That's diverging air. This is a major pattern of circulation that we're going to see again and again and again. Converging air at the surface, diverging air in the atmosphere. Another thermal circulation besides sea breezes are valley breezes. These are also formed on summer days. This valley wall can heat up quite quickly and can convect parcels up, the topographical lift aiding it. It results in a breeze from the valley and low pressure at the surface because this is rising air, a valley breeze. Oops, sorry about that. Let me go back. I have also, sorry about that. Sorry. These are the Grand Tetons. Beautiful picture right around Yellowstone. And this is a summer day where you're seeing valley lifting and convecting up on these mountainsides. Let's talk about the nighttime and thermal circulations at nighttime. It's the reverse. This is a mountain breeze at night. On summer nights, the mountain peaks cool in the altitude. The air becomes more dense here. The pressure is higher here. The air flows back down into the valley just by force of gravity. This is a mountain breeze, another thermal circulation aided by gravity. There's a thermal circulation that's very well known in the plateaus of Asia called a katabatic wind. It's known for being on the plateaus that are snowy in Asia. The winds come off here and compress and cool and warm up a bit. You see that this dense air is very cold at negative 25 degrees Celsius. It will go down the mountainside, and as it goes down and comes to a higher pressure level, it will compress and warm, and it will warm to a higher degree. That's a katabatic wind. It's a bit similar to the Chinook winds that we talked about on the eastern side of the Rockies impacting Denver. The Chinook winds are like katabatic winds. The difference is the katabatic is the plateau. The Chinook is an actual mountain range. But we're talking about compressional warming in both cases. The compressional warming on the mountain ranges with the Chinook can be very dramatic, whereas it's less dramatic with the katabatics. This is actually looking west. So you are on the eastern plateau of Colorado, looking west to the Rocky Mountains, and you are seeing what's called a Chinook cloud wall. The Chinook cloud wall is coming in from the western side of the Rockies. When people on the Colorado plains see this, they know it's about to get very warm very fast. In this particular photograph, the temperature went from 20 degrees Fahrenheit at the beginning of the night to 60 degrees Fahrenheit by dawn. That's a huge 40-degree increase in the middle of the winter. So Chinook winds can be very powerful. These are Santa Ana winds, much the same. They come down off the mountains and through the canyons of Los Angeles. Compressional warming through that area. Now you might say that's a very different direction, and it is a different direction. It has to do with the ocean currents that we'll get into a bit more. But again, this is compressional warming that really impacts the fires along Los Angeles. Desert winds really work into the obstructions around oases in the desert or around skyscrapers in desert cities. And they can come up around these obstructions onto this unstable heated surface and whip around, forming an eddy. We'll be talking more about that soon. And in regard to monsoons, monsoons are thermal circulations that are seasonally changing winds. These monsoons blow in one direction in the summer and in another direction in the winter. Let's take a look. In the summer over Asia, the winds blow from the ocean inland and bring in a wet monsoon. But during the winter, it's very different. The plateaus and the katabatic winds move everything from inland out to the ocean, and this is a winter dry monsoon. So to sum this up, atmospheric circulation patterns change over time. We talked about land and sea breezes and monsoons. We'll talk about more soon. Talk to you.